Hi, my name is Dennis Downs. I'm from CPC. We are a company based out of Minnesota, so I appreciate the snow coming down here. People here really make us feel like home. But I want to talk about who is CPC and what CPC is. I'll skip through a few things here, but what we do at CPC, we make quick disconnects for critical applications. So that's really where we focus. We do some other things that are related to quick disconnects, but our technology, our innovation, our products are quick disconnects. And so where we play in thermal management is primarily on the secondary cooling loops for HPC systems, and that's where we're focusing, and that's where we're growing and trying to continue to win. And that's why we're here, is to learn more about HPC and the needs of the market. The product shown here is a product we specifically made for thermal applications. And what that means for us for quick disconnects is a application where the connectors are connected for a long period of time but need to be ultra reliable at the point of disconnect. That's actually one of the most difficult use cases for quick disconnects, is that when products are being coupled and cycled over and over again, they lubricate themselves, the seals don't take a set. So this is a difficult application for a QD. What we have done with this product line is developed patented valve technology that allows it so none of the seals are in a friction state when the parts are connected. And that's why you can be sure that the valves are going to close at every time the parts are disconnected. So that's the real technology here that we've developed some time ago, about 6 years ago, specifically for this type of application. We've always at CPC had intuitive products. That's been kind of our core selling point since we were first founded 40 years ago. So that thumb latch, it's pretty easy to tell that's what you do to disconnect this product versus some of the competitive products that might not be as intuitive. So that's always been something that we've prided ourselves on, and that's been a big part of our company's growth. I won't go too much into the specifications here, but all of our specifications on these products are made specifically for this type of market, thermal management, whether that's HPC or some other markets. Interestingly, one of the big markets we have is in projector cooling, which it appears we maybe need today. Another thing that we have that we believe is different from our competition in this market is we have validation reports that go with our products for this market. And that might not seem like a lot, but for this market, there's a lot of questions. People don't really understand how to use these products. They don't know what is needed for a QD for these markets. It's new for a lot of the thermal architects and engineers. And so these are really, I think, the only industry reports that show exactly how our parts are validated and tested, and that's something we're proud of, and we're really transparent with these. And that goes for all the products that we make for this market. But the big technology that we believe is going to take over, that we produce, and that we believe we will always be the leaders is an engineered thermoplastic version of these connectors. This is something that's not used heavily right now. It is something that is, there's a lot of reasons why people don't think this is going to work, and we believe we've addressed all of those and then some with this product. This is by no means a low-end product, but it is a product that can scale because it's made of a thermoplastic material. The material that we've chosen is very important, and I think for all the obvious reasons, it's got to be chemically compatible. It has to be really strong and impact resistant. It has a lot of the other, it's got to be very stable in any type of humid type environment. And it has to be compatible, of course, with all the fluids typically used in these type of applications. And so that's the material itself was a big part of our R&D and innovation on this, is to make sure we had the right product. It's not the least expensive thermoplastic, that's for sure, but it is one that fits this market incredibly well. It's lightweight, it's one-handed disconnect for people who aren't typically don't know how to use a ball and sleeve or something like that. This is very intuitive again, and an easy, quick disconnect, just like all of our products. It's very stable. That's very important for long periods of time. This product has been used in aerospace applications for many years. It's been used in some plumbing applications. This material is well suited for long-term use. And then I think the biggest thing we're seeing is as people keep using QDs, they keep saying, well, I want aluminum, no, I want brass, no, I want stainless because it's the least, it has the least potential for corrosion. But the best answer for corrosion is thermoplastic. And that's why, again, we think this meets all of the needs of this market, and we believe over time this will become the accepted way to have QDs in all thermal management markets, and then that's something that we are pioneering and will continue to grow our product lines in thermoplastic QDs. Quickly, it's also V0 flame rated and has all of the needs that are we believe are needed for this market and all thermal management markets. And I believe that's it. So thank you very much.
Thank you. My name is Renee Copeland, and I work for D-Wave Systems. D-Wave Systems is a quantum computing company. It's headquartered in British Columbia, Vancouver. I'm responsible for the U.S. government subsidiary. We're located up in Washington, mainly focused on selling into the federal government and to university-based accounts. It's been around since about 1999. We've got customers that include Lockheed Martin, the Google NASA customer, as well as Los Alamos up the road. And we manage part of a system for Oak Ridge, and we've got several other customers that are remote customers. If you looked at that large black box and I stood in front of it, I'd come up to about the height of those three cabinets that are in the front. The large black container is really a SCIF. It's intended to isolate the quantum processor from pretty much everything. And if you opened it up, you'd see a lot of empty space inside, and if you remove some of the shielding, you get to this thing that looks like a long dangling Terminator arm or whatever. The actual quantum processor is at the very bottom. We use nitrogen to cool it down to about 77 K, and then we use a combination of helium-3, helium-4 to cool it down to the operating temperature, which is right around 12 millikelvin. So it's pretty close to absolute zero. And we're able to keep it at those temperatures for, in some cases, 2 to 3 years. So it's probably one of the coldest places in the universe, but certainly one of the most prolonged cold places. Outer space is roughly 3 Kelvin, just to give you an idea of the temperatures. By the numbers, I think the most interesting number on that chart is the one up on the left side, and the early applications, on the right side rather. And it should be more like 150 early applications. And these applications are what we call proto-applications or partial applications or toy applications. They're not full-blown applications that you may be accustomed to, but mainly trying to prove that you could use quantum computing for various application domains. And they fall into a couple of different buckets. Optimization is probably the one we see the most of. We've seen optimization problems solved on the D-Wave for things like taxi cabs in Beijing, aircraft routing over the Atlantic, financial portfolios, optimizing gates at airports, autonomous vehicles, satellite optimization, even optimizing schedules for nurses. We've done some machine learning, mainly trying to identify objects in 4K video stream, and a little bit of cybersecurity, mainly trying to detect things like network intrusion using lateral movement. And then most recently, we had 2 papers, one in Science and one in Nature, that were well received in the area of material science. So they are growing, and we're just delighted that people are starting to experiment with some of these early applications on the D-Wave. If you look at, the next chart can tell you where you can actually find complete write-ups on all of those applications. A lot of them come out of our user groups that meet periodically, as well as a few other projects that have been put online. The complete write-ups along with white papers and presentations are available at those locations. We do a lot of training, and a lot of the applications ideas come out of the training classes. We just conducted one for 2 or 3 days up in the DC area back in February. We've done about 40 so far around the world, more are planned. We have a user group, the European version of it held last week in Milan, 140 people, users from Europe and from Japan. The US version of that user group will be in September, probably up in the Rhode Island area. And we also do seminars. This is year number 6 of doing a couple of days of what we call the DC seminars. So if you find yourself in the DC area next week, we'll be doing one out by Fort Meade and another downtown at the W Hotel. It's a half day, about a third of it devoted to presentations and about a third devoted to lunch, and the rest just to networking and interacting. In October, we announced our cloud access. We call it LEAP. We sort of formalized this remote access that had been going on for a long time. It's free. I'd encourage you to use it. You'll find a lot of tools there that'll simplify the programming process a little bit, and a lot of explanations in terms of how things work. We've been on a path since we started to kind of double the qubit count every few years, and the qubit count is just one metric, probably not even the most important metric for quantum computing, but we're currently up to about 2,000 qubits. And I should point out that you shouldn't try to compare the gate model-based qubits with the annealing quantum qubits that we are using. They really are different, and the numbers don't give really a representative comparison. But if you were to look at one of our qubit chips in this particular representation, it looks like what the graph theorists would see. The dots are qubits, the lines are connectors, and there are actually a few missing qubits in the middle of them, so it's probably a real mapping. If you looked at, zeroed in on just one of them, what we call the unit cell, and then started to make some changes to that unit cell by adding some additional couplers, adding a few additional qubits, displacing the qubits vertically, displacing the qubits horizontally, pretty soon you start to see a pattern that doesn't make a lot of sense to you. It just sort of, looks very convoluted, but it really starts to evolve into what we're calling our Pegasus architecture, and this is representative of the next generation, which will be out next summer. So we are going from that topology, which is called Chimera, to that topology, which is called Pegasus. And in doing that, we increase the qubit count. More importantly, we increase the coupler count. We managed to get the connectivity up to about 13. Noise goes down quite a bit. We change the materials from niobium to another material we're not talking about too much, and we still maintain the power profile of about 20 to 25 kilowatts, which is about as much as we have in this room. And that's been the profile since inception. We really don't use a lot of power, particularly when compared to some of the exascale kinds of projects that we talked about earlier today. One quick drill down into an application. Ocado is a grocery store chain located in England, and they are probably the largest online grocery service, but no one's ever heard of them. But they have about 1,100 robots, and they scurry around trying to fill orders. The containers below the robots, about 250,000 of them, are full of groceries. So the idea is you call, and within 5 minutes they want to fill your order. So lots of opportunities for conflict, for traffic jam, catastrophe possibly if not done correctly. But they started to use the D-Wave, and they were able to actually prove that they could optimize the robots within the warehouse using a combination of D-Wave and classical systems. And I show that not because you're necessarily interested in grocery stores, but that's a grocer in the United Kingdom that's starting to explore the use of quantum computing. So if you're a computationally differentiated organization, we would strongly suggest that now you start to work with us, or even some of the other vendors that are in the space, to get ready for the next couple of years, where you will probably start to see a competitive advantage in quantum, particularly with the passing of the National Quantum Computing Initiative. Thank you.
Hi, my name is Dr. Radoslav Danilak. I'm founder of the Tachyum. Tachyum is a semiconductor company focusing on hyperscale cloud, but also we have customers in HPC space. What we do, we are designing chips. We are semiconductor play. We build, I will provide you more information, universal processor. Universal means you can run existing workloads, high-performance computing workloads, AI workloads, and other workloads in single piece of the silicon rather than having whole zoo of the accelerator at similar efficiency in performance per watt and per dollar as these GPUs or accelerators. Our primary market is hyperscale processor market, and we have products specifically for that, which will have prototype this year and be in production next year. We have variant of that same piece of silicon for high performance computing, and I will talk a little bit more about that on next slides. So one of the problems what we fundamentally are solving is that the reason in last 10 years the clock speed of processor did not grow up, despite the fact that transistor become faster, the issue was that wires become slower and slower, thinner and thinner, more resistive and so on. So we came with the solution where we come with a computational model which is taking into account physical location, topological location on the chips. So instead having computation, addition and communication, moving data around as part of one cycle, we separated computation from communication, and we built the compiler to place and route communication in the way where it removes the wire from critical path. Now, why do we say it's universal processors? Because we support conventional workloads. We have GCC compiler, and we'll have next year LLVM compiler, of course, Fortran compilers, as well as TensorFlow for AI and high-performance computing. So the only reason why people use GPUs or accelerators, because the performance per dollar and performance per watt is better. That's the fundamental driving reason. And the downside is the pain, is difficult programming model of FPGA and so on. So if you can come with programmable solution with similar programming model as the CPU, but with performance per dollar and per watt comparable to accelerators, then basically there will be significant benefits. So in our case, we can run multiple disciplines of AI, not only deep learning, convolutional network, but also explainable AI, bio AI, and many other disciplines. A little bit about the chip. Our chip is a 7-nanometer device, which has 64 processing core, which each core is faster than any other core available, including Xeons. Supports 512-bit vectors, double precision, single, half precision, narrow precision. Has HBM interfaces, 8 DRAM interfaces, DDR5, and 400 gigabit Ethernet to connect system to cluster of 65,000 nodes and so on. One of interesting angle relatively to HPC computing is that our customer hyperscalers, they would like to utilize the resources for more than a single task. What you can see is the 24-hour cycle on the Facebook, how the servers and chips are utilized. And what we can see, it's built for peak demand, where the average utilization is less than 40%. And then Facebook has GPUs for training, which run 24/7, about 5 to 7% of the machines. Now, with our chip, rather than having 60% of machines idle, you can run training on them at similar efficiency, outperforming, for example, NVIDIA Turing. So suddenly, without spending additional money, our customers, they can get 10 times more AI reusing existing hardware, bringing from 40% utilization to 80% of utilization. So that's our value proposition. The last comment, we will have the proto system FPGA later this year, and we should be in production in 2020. Our single socket replaces about 4 conventional sockets, so there is good benefit from power and cost. And if you want to know more details, you can look in Microprocessor Report, published the article we presented last year on hot chips, and we will be providing more information. Thank you.
Hi, I'm John Unthank with IBM and IBM Federal. And let me start by saying there's been a number of IBM topics throughout the last couple of days, and if you need additional information or need to find some connections into IBM, feel free to reach out to me and I'll help you get established. Big company, and sometimes it's hard to get started. The IBM Spectrum Computing Software Organization funded the participation and sponsorship of the HPC User Forum. So I'm going to show them some love in this presentation and talk about a project that they're involved with. Over the last few days, we've heard a lot about containers and HPC, so hopefully it'll be something that you can connect with. They have been providing our sponsorship with the HPC User Forum since they joined IBM back in 2012, which was my first HPC experience. So they've been a consistent partner, and we're happy they continue to fund our activity here. So in the world of containers, it's workload that must be scheduled. It's typical in the HPC space to have a high-performance workload schedule. The IBM technology is called LSF. It's mature technology, very rich scheduling policies, very flexible, supports bare metal partitions and now containers. Container technologies include Docker as well as the DOE developed containers, Singularity, Shifter, and Charlie Cloud. So it's a very robust scheduling capability. Kubernetes, as a scheduler, is developed for Docker workload. It's quite powerful, but it's new. It's not as feature-rich from a scheduling perspective. It only supports Docker, does not support bare metal. It'll get there, but there's lots of activities that need to develop. Their scheduling policies are primarily first come, first serve. So IBM is a strong participant in the Kubernetes movement. We have built our IBM cloud offerings on Kubernetes. We have significant financial investment and make significant contributions. So this is in no means trying to slight Kubernetes, but it opens up an opportunity to leverage both scheduler types to get the benefits of both worlds. And I'll talk of two particular methods that we're providing in a technology preview. The first is for those that are HPC specific with LSF Scheduler, that you can add Kubernetes workloads on top of nodes in your LSF cluster, and they can provide the Kubernetes services. So you're able to blend your containerized workload with your HPC workload, taking advantages of all the functions in Spectrum LSF. LSF is very scalable. It's the workload scheduler on Summit and Sierra, so very large environments that it manages. IBM continues to invest in scalability and performance and new function in LSF. The other direction of support is where you're coming from a Kubernetes world, where you can put LSF in a container managed by Kubernetes, and Kubernetes has the flexibility as to which schedulers used to manage their pods. And so it allows you to take advantage of the advanced scheduling capabilities in LSF running inside a Kubernetes environment. The technology preview is a free download. You'll get these charts so you can try the links, so you can reach out to me or do Google search. But it gives you the capability to do the types of integration we've been just describing. In addition to managing the containers, there's also a need to feed the storage environment. And so we've extended IBM Spectrum Scale, you may still recall as GPFS, so that you can use both LSF and Kubernetes as the ability to manage and schedule data and provision data for your containers. Along with work with Kubernetes containers, we continue to expand functionality of Spectrum Scale, very significant investment, where it's far more than just a file system today. We support cognitive workloads with recent certifications of things like SAP HANA, the NVIDIA technologies for AI, Cloudera, Hortonworks, Hadoop file system replacement. So it gives you the capacity to create data lakes to marry together both your HPC and analytics workload on a common platform. You'll see on the chart there's an active spectrumscale.org user group. Their next meeting is April 16th and 17th at INCAR. If you have an interest in Spectrum Scale GPFS, I'd encourage you to join. There's no charge. And all the presentations from future and past meetings can be found at their website. Thank you.
Okay, good. Hi, Curtis Anderson. I'm with Panasas. So before we get to my presentation, just in case you're not familiar with Panasas, we're a parallel file system, one of the granddaddies of the category, founded a long time ago. We're a heavily engineering-focused company. We are in the middle of transitioning from our proprietary hardware platforms to commodity hardware platforms. We're about 2/3, maybe 3/4 done with that at the moment. But in keeping with the theme of this week, or of today, I'm going to go through what I hope is not Captain Obvious, but still, metadata is not data. Virtually every aspect is different, and we need to treat them as different things. So, mind is my cheap mnemonic for to try and get people to remember this, that metadata is not data. There really are different things. It's not the one is a byproduct of the other. They're functionally different. Their access characteristics are different. They need to be treated differently. I threw in a comment here about archivists. I heard the first time I heard the term provenance was 20 years ago, and it was in terms of Library of Congress, that they need to keep old pieces of technology like VisiCalc. That's an archived item, so they need to have not just the software, but the 5-inch floppy disk and the reader and the computers it ran on, all of that together, CPM and everything, in order to archive that thing. So I thought that was a cute thing. So here's my attempt to really bring home that metadata is just different. All the access characteristics are different of it, but between it and data, not just the purpose of it. Give you a second to look at that. I'm not sure what else to say. I mean, this is that everything's different about it. It's not like Captain Obvious, right? It's not, you don't really think about it until you look at it in detail and say, yeah, every characteristic is different. So why did we get here? And then I'll get to what Panasas is doing about it. Metadata has grown from, it was just the inode attributes. And then along came extended attributes, and along came other things. And because of that history, we all think of it in terms of POSIX and the POSIX APIs that gave access to them. But those were metadata was an afterthought, right? There's 5 different variations of read up there, and there's just the one stat, fstat and lstat, not really different. DMAPI made an attempt at distinguishing, providing a bulk stat operation and started to operate in metadata. But not many people are like DMAPI for some reason. In addition, metadata was stored inside a file system, and so the file system implementers tended to use file system techniques to manage the metadata, which was great if all you were interested in was the data. Metadata was an afterthought. So parallel file systems have always separated metadata from data, metadata processing from data processing. At least in the case of PanFS, the metadata was stored as uninterpreted blobs that were stored on the storage nodes proper. It's because it was only the director nodes, the metadata processors were stateless, and that was a good thing. We are in the process with our next generation, moving to our storage node to new commodity hardware. We're taking the opportunity to rewrite essentially the entire piece of software, and we're continuing to separate metadata from data. So you can see the diagram on the right. That's the sort of the block diagram for the software. The thing that's relevant here is the little column in the left there is metadata store. That's a completely different access characteristic, different software management technique for metadata from user data. The metadata needs fast atomic transactions, consistent performance, optimized caching, and intelligent queries. So one of the consequences of our separating metadata in our storage nodes is that in the future we'll be able to do things like I want to find all the files that Joe owns that haven't been accessed in over 12 months and are greater than a gigabyte in size. Well, we could do MapReduce. We can send a query out to all 600 storage nodes, pull the data out of each individual database, and send it back, and then sort and filter, and give you an answer. So that the metadata processing, at least our piece of the overall universe of metadata processing, our piece of it is high performance and optimized.